Hey everybody, welcome back to the Chemistry Podcasts. This is the last podcast for Unit 9, Podcast 9.4. Today we're going to be working on ideal gases and Dalton's Law and Graham's Law. So to help me out today, I've got two helpers, Amanda Lindsay and Lindsay Ritz. Y'all say hi.
Hi.
Let's see, Amanda and Lindsay. So I hope you guys are ready to work. Get your packets out, follow along in your note-taking packets because we have lots to accomplish today. So, yep, that's Amanda's name. She's all excited because I spelled it right. Yay. All right, now I got to get my tools back. What happened to them? I hate it when that happens, when they go and disappear. Yeah, we'll be moving on in just one moment as soon as we can figure this out here. Quick. I hate
A little
this.
clicker thing?
No, that's not the thing I want. I just got to go back to get this. Well, hello, computer screen. We'll just use the laptop. We can figure this out.
Awesome.
We're good like that. All right, so the ideal gas law basically tells us that we can predict the behavior of any gas under any conditions. So if you know pressure and volume and temperature, then you could calculate moles. Right? So all we need is 3 and we can find out the 4th. Okay, well, we know this gas law as Pivnert. You guys remember Pivnert, right?
Yeah. Too well.
Too well? All right, well, what's Pivnert tell us?
Everything.
Everything. Yeah, anything you want to know about a gas, we're going to use Pivnert for. So basically it says PV equals what?
NRT, also known as NERT.
NERT. Right, that's the NERT side. And then this is the PIV side. Pivnert. It sounds so dorky, but it's going to be very useful. Yeah, that's not the one I want. It gave me an eraser. Wow, that's amazing.
Get
Okay,
my clicker things back.
I got my arrows back for some reason. All right, so let's look at pressure. You guys just learned how to convert units. For Pivnert, you must either use kilopascals or atmospheres. You may not use millimeters of mercury for this one. The V stands for volume, and volume has to be in liters, not milliliters, right?
Yep. Right.
Okay, good. And then what does N stand for?
Number of moles.
The number of moles of your gas, not just moles of any old random thing, the moles of your gas. And then R is something we've never seen before. R is something we're going to measure in a gas lab. We're going to measure it. We are going to measure R in your gas law lab. It's a constant, so it's a number that doesn't change. But we have two different versions of R. Do you remember what R is if we're measuring pressure in pascals?
8.31.
Yeah. Or that 8.314, but you guys don't have to know that in your sick face. 8.31 if we're measuring in kilopascals. And those are SI units for pressure. But we commonly use atmospheres. Do you have that one, Amanda?
0.0821.
There you go, 0.0821. You like how I put you on the spot. Think fast.
Put me on the spot.
Yeah, well, you studied this before. It's only been a year.
No big deal.
Yeah, no big deal. All right, well, the key to Pivnert, or the ideal gas law, is that it describes the conditions of gases as they are now. The gas laws that we used before told us what would happen when they change. Like Boyle's law keeps the temperature constant but changes pressure and volume.
Macaroni.
Macaroni, don't let your macaroni boil or something like that. I don't know.
I've never heard that before. Moving on.
Yeah, oh, clear the writing because that looks weird. Let's do an example because the easiest way, I think, to learn something is to just do it. All right, so here we've got, oh, this is a hard question. How many kilograms of methane? So here is our target, kilograms of methane, are in a 225-liter container at a pressure of 150 kilopascals and 35 degrees Celsius. So let's break out what do we know. First, we've got pressure, and since it's in kPAs, then which kind of R value do you want to use here?
The 8.31.
Good plan. 8.31. And these girls see me nodding my head and you guys don't, so I'll stop doing that probably. Or maybe not, I don't know. Hard to not nod when they get it right. And here's our volume from the problem, 225 liters. And then temperatures, we need to convert to kelvins, because this is a gas law after all. We better convert to kelvins, right?
Everything's in kelvins.
Of course. So we know that we're going to use this equation. PV equals N times R times T. And you girls can get your calculator together. But our target is kilograms, which is mass. And in PivNert, I have nothing that refers to mass. Do you see any way that we could get to the mass?
How about we use moles?
Oh, all right. So our plan is we're going to use moles and convert to the mass. Okay. So let's solve for n first. You see, to get n by himself over here, we're going to do algebra. You ready, Amanda? Divide both sides by RT. On this side,
And they will
they
cancel.
cancel. And on this side, we end up with n equals PV over RT. Wow.
That's not the R.
You don't like how that looks?
No, the other R. That
Oh,
R.
you want that gone? Yep. All right, there you go. So we have PV over RT. Let's put our values in. P is 150 kPAs. We're going to multiply that by the volume, 225 liters. Oh, I don't need to write in all my units. And then we're going to divide by 8.31. And then in your calculator, when you do this, you're going to like divide again, right? Or use parentheses around this whole entire thing when you multiply them together. Temperature has to be in kelvins, 308 kelvins. Whoops. 8, there we go. And then I'll make sure that we do the order of operations correctly. Okay, what you get?
I got 13.1863.
13186.3. All those numbers?
Yeah, put
We
a,
need a decimal here.
of course, because that's way different than 13.
Yep, it is. And for now, let's keep all of those sig figs. We're not going to round until the end.
Okay.
Could you round after the 3? There's more. Oh boy. Did you round correctly?
Of course.
All right. Well, I don't think that's going to make a big difference with our sig figs. So now we have to get to the mass. We're going to do a t-table. Whoa. Doesn't like me sitting there touching the screen. So 13.1863. Just keep that number that's in your calculator. And we're going to change moles of methane to kilograms of methane. Well, I know how to change moles to grams. So let's real quick add up the molar mass of methane, which is CH4. Let's do this in your head because you're so good. 12 is for carbon, and each hydrogen is worth 1.
So the mass would be 16.
16 grams per mole.
You're good, Lindley.
I know.
Yep.
So good.
All right. And we have to change grams to kilograms. So grams has to be down here and kilograms on top, because that's the way we're going to get grams to cancel. Since kilogram is bigger, I put the 1 there, and there's 3 steps, so it's 1,000 grams per kilogram. Okay, Amanda, you're running the calculator?
Yes.
So take what you got and multiply by 16. And then divide by 1,000, if you would, please.
0.21098035554.
Oh, dear. I don't think we need all of that, because what we started with up here in the problem, we have 3 sig figs here, 2 and 2, and so we better quit right here. Is that 0 going to make any difference?
No.
Nah. So we'll just drop that off, 0.21 kilograms. And you're checking our answers, right, Lindsay?
Of course.
Good. Are we doing it right so far?
You are.
Brilliant. I love it when we get the right answer. Good job, Amanda.
Hopefully I'm not too
Thanks.
far away.
All right, now look at all that messy writing. The ideal gas law works for ideal gases, right? So how do we know if a gas is actually an ideal gas? Well, here's the criteria. The ideal gas law has to follow all of the gas laws at all temperatures and at all pressures in order to be considered ideal. So Boyle's law, Charles' law, all those dead white guys and their laws. Yep, got to follow all the gas laws at all temperatures and pressures and never deviate. An ideal gas should also conform precisely to all the assumptions of kinetic molecular theory. Remember, that's what is describing the collision of particles, right?
Of course.
Yeah, we talked about collisions and how to get a prom date in AP chemistry.
Brandon.
So if he doesn't have a prom date yet, we might need to add a catalyst. His prom's coming up soon.
Danny's a great catalyst.
All right, particles have no volume if they are ideal gases. In other words, the molecule of gas should not take up any space, because then that would alter our calculations of the total volume of the gas. Right?
Correct.
Okay. Last criteria, there should be no intermolecular forces acting between the gas particles. So do you think we can eliminate every single IMF?
No.
Right. In fact, we can't accomplish any of these things. Ideal gases don't really exist. But for most temperatures and pressures, the ideal gas law works so well that we're going to use it anyway, even
we
though
can.
there is no such thing as an ideal gas. But in AP chemistry, you learn how to adjust for these criteria. So in a real gas, we have to we have to factor in particle size. Bigger particles take up more space, and so we have to consider that. Consider, like, hydrogen gas is made of exactly 2 protons and 2 electrons. All right, so now let's compare that to something like chlorine gas.
Polonium.
Yeah, well, polonium doesn't typically exist as a gas. Not at room temperature anyway. Good luck vaporizing that.
I'm a chemist. I can do anything.
That's right. That's why they pay chemists the big bucks. All right, now chlorine has 35 protons. And, no, 34. Yeah, because 17 plus 17 is usually 34. Thanks, guys, for your backup there.
Welcome.
Yeah, 34 protons for this diatomic. That's a P plus proton. Gosh, criticizing my writing. And 34 electrons. So which of these 2 particles is going to take up more space?
Chlorine.
Obviously, right?
Little
It's
bit.
got a lot more stuff in there, so it's going to take up more space. And that's going to deviate more from the ideal gas law.
I thought those were both Brinkelhoff.
I know, I did that on purpose,
Oh.
because they're diatomic gases. I want to make sure everybody's got that down, that Brinkelhoff thing.
Wink, wink.
Yep. All right, another thing we have to look at is the IMFs between the particles. Some particles are polar, so they have a positive side and a negative side, like that water molecule. And so we have to consider the attractions between charged particles on one side of the molecule for another. So water would be able to form hydrogen bonds. That's a pretty strong intermolecular force. Agreed?
Agreed.
Right on.
Nodding doesn't help out.
Right, everyone watch Lindsay nod. Maybe I could draw my arrow up and down. Yep, she's nodding now. Yep, there goes her head. Yeah, doesn't help us understand. Sorry. Okay, so when would an ideal gas be most different? If we could get the particles really close together, then we would be increasing IMFs, right? And then the particle size would be a bigger factor if the particles were closer together. So if we squish them really close together, so high pressure, we would have a bigger difference. What about the temperature? How could we get the particles close together? If we raise the temperature or lower it?
Lower it.
Why would that get them closer together?
Because it would slow down their kinetic energy so they wouldn't move as fast.
Right, they don't move as fast, they don't collide as much, and so they can get closer together. Good call. The real gases is what gives us the true picture of a gas, and we can make adjustments for this mathematically that work very well in making predictions of what will happen chemically. Oh, and I always forget to clear the writing. Yeah, it looks really weird. Well, let's look at what happens when we have a mixture of gases. If we have two or more gases together, then we have such a thing as partial pressure. In other words, the pressure existed by just one of the components of a gas. And we got a simulation ready for everybody to see. So let's have a look at that, if I can find it. There it is. Some of you guys got to play with this in class today, and so you're already familiar with what this looks like. But let's put some gas in here first and see what happens. So I'd like you all to keep your eyes on the pressure gauge. So how many particles did I put in there? 88 particles of our smaller gas species. And notice how they go bumping around in there. And our pressure is shown on the pressure gauge right here. So this is what we're watching. Oh, you like that black circle? Yeah, okay, clearing that away. Maybe we need a different color. Should we use red or green or something?
Pink.
Pink, but it's broken.
Yellow.
Oh well. We'll use
We
pink.
pick pink instead.
Pink broken line. So here's our pressure gauge. We're watching this. You ready to add some more gas?
Yes.
Of course.
All right, well, I want to be fair. I have, oh, geez, did one escape already? I thought we had 88. Oh, well, we'll put 88 more particles in
You see it.
through this pump of gas. There we go. So now we have, how did I get more?
You pumped it, so.
Oh, well, oh well. Just let's remember what we had. 121 little particles. I'm going to write it down because I'm going to clear them all out. 121. That's arrows. How clever. Why did you pick pink?
I like pink.
All right.
Like
Yep.
yellow.
What do you know?
Go green.
Yellow.
Pink is an
Go
arrow.
green. Save the
Okay.
planet,
Let's
go
do
green.
green because it's an actual pen we can use. Okay.
Green.
So we have 88 of these and 121 of these. Gee, many. Oh, look, that is an arrow. It was one arrow all along. Yeah, I can't speak. Don't make fun of me. All right, so here we go. Let's take out all of our gases, reset, and let's look at one pressure at a time. So how many light species? 121, right?
Yeah.
Yes.
Okay, there they are. They're going in there.
Okay.
And what's our pressure for just this particular gas?
Hanging around 0.6.
Two.
2, yeah.
Okay, so it's sort of going back and forth. Why do you
Right.
suppose it doesn't just stay at one number?
Because at any given time it depends on the number of collisions.
Right. How many particles are colliding with the container at exactly that moment?
That's exactly what I said.
Yeah, you sounded so smart when you said it too.
Um,
All right, now
well,
let's
you
do our heavy species.
Learn from the best.
88, right?
Yes.
Okay, there they go.
Off to the races.
All right, we'll
Slow
let them
races.
bump around for a while. Let our pressure stabilize. We good?
0.4.
6,
Okay.
Go, yeah.
4, 6 is a good estimate.
5,
Go 5.
6, 5,
6, 7.
Let's go 5.
All right, we'll
5, 5.
go with 5 because that helps us anyway to figure out what's going on. So in a mixture of the two gases together, what do you think the pressure is going to be if I put them both in there at the same time?
It would be the total pressure of
So we just add these two together?
Yep.
All right, well, let's add them. Carry my one. About 108. And are we going to get up that high?
maybe.
Yeah, maybe. Pretty close.
Close enough.
We're pretty
Yeah,
darn close.
we're at 1.05, 1. Oh, back under 1. Yeah, that's pretty close. Why do you suppose that an experiment doesn't match what we predict?
Because it's an experiment and they don't like us usually.
And are these ideal gases?
No.
Of course
No,
not.
we just talked about that. These are not ideal gases because there is no such thing. Especially the blue guys, since they're so big and take up so much space, they are more realistic and less idealistic. Ooh, that's kind of fancy. Ooh. All right, well, let's see what our notes say about that. Yeah, we better go back there because I just saw the notes flying in. There we go. And there's our writing.
Nice.
Yes, isn't it?
So those blue particles would be like the chlorine gas?
Right. And the red particles would be more like the hydrogen gas. And Dalton's law says that there's a law of partial pressures. For a mixture, the total pressure is the sum of all the partial pressures of a gas. And so you called it just correctly. Was that Lindsay who said just add them up? I believe it was. Good one.
Yes.
Good thinking.
Stop nodding.
The first name Lindsay, not the last name Lindsay.
You give them my identity.
Oh, I
Stop it.
totally did. Sorry. Yep, now they're going to track you down, stalk you. So the total pressure of all of the gases in our mixture is equal to the sum of the pressures of each. But what if I just wanted to find one of the pressures? Let's do a problem like that. Do we have a problem yet? No, not yet. We'll skip ahead until we do. So, no fair copying down the notes yet, because we'll come back. No, we won't. What did I do? Do you have a problem on your page? I thought you did. I thought I added one in. All right, well, we'll just insert a blank slide right here, no big deal. I think I can do that. Add blank slide.
No way.
All right, give us a problem, Amanda.
Dalton's law, example problem 1. Determine the total pressure of a gas mixture that contains 20 kilopascals of oxygen, 46.7 kilopascals of nitrogen, and 26.7 kilopascals of hydrogen.
All right. You're going to have to read that again. I had 20 kilopascals of what?
O2.
Just 20 or 20.0?
20.0.
Okay, I got to keep track of my sig figs.
Thank you, Lindsay.
You're welcome.
All right, 20 kilopascals of oxygen,
46.7.
46.7 kilopascals
Of nitrogen.
of nitrogen. Okay, more Brinkelhoff elements here. Oh, you like that equal sign. Let's see, equals. All right,
And 26.7 kPa of hydrogen.
They're all Brinkelhoff.
they are. A lot of our elemental gases are Brinkelhoff elements.
Stinker.
Yeah. Okay, and now we have to find the total pressure for all of these. Well, this shouldn't be too bad, right? What do?
You use Dalton's law and you add all of the pressures up.
Add 'em
Yeah.
up.
Exactly. So we're going to take 20.0 plus 46.7.
Oh, I
Oh,
think they can
there,
hear
get
me.
the calculator. Yeah, they can hear you eating your mint, I'm sure. And then 26.7. I just ratted you out. Did you notice?
You guys don't get any.
No, not in the chemistry lab. All right, what'd you end up with, Amanda?
93.4 kPa.
93.4 kPa. Now let's compare that to atmospheric pressure at sea level. Is this, let's see, normal pressure in kPa's would be 101.3 at
I
sea
remember
level.
that.
Yep. And this number is lower than that.
Yep.
Yeah, but not much lower. So this mixture could be actually a realistic mixture for gases, say in Falcon, right? Where this is about what our atmospheric pressure is because we're higher in elevation than sea level. Now, we'd have to do a calculation to see what fraction is nitrogen. If it's about 80%, then it would describe the atmosphere on Earth, right? Because it's about 78% nitrogen and 18% oxygen, and then the rest is a bunch of other little stuff, like water vapor and xenon gas and all that. Are we anywhere near?
You're like half.
Yeah, that would not be a good atmosphere to live in then. Let's do another example problem. Do we have an example problem too?
Yes.
We do.
All right, because I think in the gas law lab we do, they're going to have to know how to do something more complicated than just adding pressures.
Is that a complicated? Maybe.
Yeah.
Go, little computer,
Oh.
go.
I know what I need to do.
Oh.
Clear my writing. That's what. All right, so here's example 2. And you guys might not have this in your notes, but just like I did, I found a space to write it. And so all you guys following along at home, find a place to write these down. Go ahead.
The following reaction takes place in a sealed 40.0 liter container at a temperature of 120 degrees Celsius.
So 40.0 liters is my volume, and my temperature is how much? 20?
120.
100.
Oh, 120, that's a big difference. And that's degrees Celsius. We'll be converting that. All right, I'm listening still.
Now we have an equation.
Okay, here's our chemical equation.
4NH3
Okay, 4 ammonias,
gas
of course, since this is gas unit. All right,
plus 5 oxygens
this looks like a combustion reaction. Adding oxygen. All right, what are we going to make?
you yield 4NO
Mm-hmm.
plus 6 waters.
Okay, and these are all in the gas phase?
Absolutely.
Of course. And 6 waters. All right, and of course we've double checked to make sure this is a balanced equation, right?
Of course.
Naturally. So that would be our first thing to do. And what's our question? What are we trying to find out?
When 34 grams of ammonia reacts with 96 grams of oxygen, what is the partial pressure of NO in the sealed container?
And it's reacting with 96 grams of oxygen?
Yes, ma'am. 0.0 grams.
Oh,
But
point
that's,
0 right here.
that's
Okay.
cute.
Thanks. I thought that was good. Then what is the what? What are we doing?
Partial pressure
Okay.
of NO.
Of NO in the container.
Mm-hmm.
So that's our goal. Are we given any other information?
No.
No.
Yeah. Since NO is not the only thing that's made here, we also need to know the pressure, the partial pressure of the H2O. And we have a table where we can look up what's the pressure of
Onward.
H2O, water vapor, at any given temperature.
Is it the regular chem book? Or would it be AP chem?
Actually, it's in the gas law lab. So,
Oh, crap.
yeah.
Did you know that you can pause?
I did know we could pause the recording. I just don't do it very often because everyone else has to write this down anyway. All right, so this is one of those really long problems that brings up a lot of concepts from everything we've ever done. Because we're going to have to use PIVNERT so that we can calculate pressure. And before we can do PIVNERT, we need to know what N is, how many moles.
Oh, I remember.
Yeah? Or, yeah, we have to, because we're not at standard conditions. Because if we were at 1 atmosphere and 0 degrees Celsius, we could just call it 22.4 moles liters per mole.
We don't have it for that
But we're not.
temperature.
We don't have it for that temperature?
Let's make it up.
Yeah, probably not.
Let's make it
I don't know. We'll just solve this for the one gas at a time. And it's NO, and we won't worry about water because they didn't ask us for water.
Nope.
Right? Okay, let's convert temperature to Kelvin. So 273 plus 120. You can probably do that in your head.
What is it?
120 plus 273? Using a calculator in your head.
393.
You knew that.
Of course.
393 kelvins. Then we've got to get to the number of moles of NO. And here we know we started with 34 grams of ammonia, and we also started with 96.0 grams of oxygen. Which one runs out first?
We don't know yet.
We don't know yet. We're going to have to do a limiting reagent problem. So we know 1 mole of ammonia has what molar mass? 14 plus 3?
17.
There you go. Using the calculator when you don't need to.
There you go, Sparky.
Yeah. All right. And then let's apply our mole ratio. So how many moles of NH3 does our equation say?
4.
All right. And we're changing it to moles of NO, and that's also 4, isn't it?
Yes.
All right. Well, that's easy math. 4 over 4. I could do that one in my head. Amanda's going to use her calculator.
Watch me.
Just messing. All right. And then, hey, we just wanted to go to moles. I can stop now. I've got all this big, long mess over here for no good reason.
Just click the little thingy. No.
Probably so.
You make things so difficult.
You make my life difficult. But I keep you around anyway.
That's good.
Yeah. Okay. So we'll do this one, and we'll do the same for oxygen, 32 grams per mole. Because it's O2, right? That Brinkelhoff thing. Got to pay attention to that. And then what does our balanced equation say about this?
We have 5 moles of O2 in the equation.
Okay. And we still have 4 moles of NO.
Yep.
Make sure that you put oxygen crisscross so that we can get those moles to cancel. So NO goes on top and O2 goes on the bottom.
And then we're done.
Yep, and then that part's done. And I could erase this. And Amanda says I can push the clicking. Oh, she's so right. You are so smart. It's kind of annoying sometimes.
Yeah.
All right, what do we have?
For the first one, I got 2.
Okay, 2 moles. Yeah, that makes sense. Look, 34 divided by 17.
Woo!
This page doesn't have an answer.
This page doesn't have an answer. It must be a hard one that I didn't want to solve without your help. 2 moles of NO. All right, do 96 divided by 32. That might work.
How about 96 times 4 and then do 32?
How about I just give you
Alright.
the answer of 2.4?
2.4, okay. But we want to make sure everybody knows what math you did, right?
You don't want to do like 96 times 32 and then multiply that by 4 and get 5 because you might, I don't know what answer
Yeah.
you get. You might get the same, but
The biggest problem here is that often we multiply the top times the top, and then you divide by the bottom. If you put this in your calculator, you say, okay, now take that answer and divide by 32 times 5.
In parentheses.
and then that's
Yep,
going to
make
be
sure
wrong.
this part is in parentheses.
Yep.
Because your calculator thinks you want to do this first and then multiply that answer by 5.
And then you're going to get
You're going to get a
Crazy
wrong
number.
answer. Yeah, we want to convince the calculator to do things our way. So use parentheses there. So which one ran out first?
Ammonia.
Right, ammonia's our limiting
NO.
reagent. NO didn't run out. We made some. And this is as much as we could possibly make. Did you make 2.0 moles?
Yes.
Good. Well, now let's solve for the pressure that ammonia, sorry, that NO, nitrogen monoxide, has at these conditions. So we don't want to know what it's changing to. We want to know just what it is. So we're going to use PV equals N, come on, little pen, nRT, where we want to get pressure by itself. So divide both sides by volume. And now we are ready to put numbers in. So we have 2 moles. And what's our units for pressure?
Are we in
KP.
We don't know. Which one do you want to use, atmospheres or KPAs?
atmospheres because I like that one better.
Okay. So it's 0.0821, and that's liters times atmospheres over moles Kelvin.
K-mole.
That one comes up a lot. And then T,
It's all coming
temperature, we
back.
changed to kelvins, 393 kelvins. And then we're going to divide all of this stuff, this whole entire mess, by our volume in liters, which is 40 liters, because our container is 40 liters. All right, so what's our pressure of NO?
User error.
User error. It happens to the best of us.
1.613265.
1.613265. How many sig figs do you want to keep there? 3?
Looks like 3.
Yeah. Sometimes our book is not very specific about.
Or 2.
Isn't that just 2?
Yeah. It would be 2 because of this temperature, and because of these masses, the 34 is only 2. So
And the volume is only 2 as well.
Nope.
0 doesn't count.
does both zeros count?
Aw.
Yeah, because any zero between 2 sig figs counts. So,
That's new.
nah, not new. It's old. It's just an old rule, and you've got all this new knowledge taking the place of old stuff.
No kidding.
So we're going to call this 1.6 atmospheres. So is that more pressure than sea level or less?
Say what?
Is this more
More.
pressure than
More.
sea level or less?
More.
What's pressure at sea level?
Wouldn't it just be 1?
Yeah, it's just 1 atmosphere. So this is like 60% more.
I hope they can hear me actually say that.
Oh, yeah, I hope so too.
I'll just take it and
Yeah, you can mess with the volume for us and fix our podcast. Eventually, we're going to get really good at podcasting.
we're gonna have to shout at the computer
So,
pretty soon.
all right, well,
We can start singing.
now that we've had some practice, how do I go back to my slides before? So that, wrong button.
It's like Nemo. Touch the
You said butt in my podcast. Gee whiz.
button. I heard you. They didn't hear
Ah.
me.
On this slide, actually,
Here's where we are.
on the problem slide,
Yeah.
it said to find the total pressure as well.
Oh, so we did have to do the water.
Oh well.
Gosh, all that work, and I just erased it.
Click the undo.
That's your homework.
That should be the homework.
Yeah!
That's
That.
right. Good call. Here it is. It's all
You
back.
guys got lucky on that.
All right. So how would we go about solving for the total pressure? We would do the same thing, do the limiting reagent problem, only now we know which
Except
one
now you're gonna
is the
change
limiting reagent.
the formal right
Mhm.
here to that's not helping anyone if I'm pointing there.
Yeah, pointing with your finger at the screen, but
So
not
just change the
anything.
pen to like red.
Okay.
I'd
Green.
probably,
I
I'd
like
probably
green.
just
Let's
change.
just do this. We want to go to the
You
same
want to keep
place,
that 4 on the top.
but
There you go. Just use the cookie thing on the pen.
oh, I did the wrong. Yeah. Okay. We still want. I'm clicking it. Oh, and it's not doing anything. We still want 4 ammonias. I erased the wrong thing there. But
Oh,
now you
now
want to go to
you want-
waters, right?
Yes.
Okay. How many waters? 6 waters.
6 moles of water.
Okay. So everything else in our T table, you want to just keep the same?
Yes.
That ought to work.
And then just get rid of the 2 and the NO.
All right.
Yeah.
So we still have 2, but now we're multiplying it by 6. Did you get 12 moles?
What?
In water?
I definitely got 3.
Oh. Oh, yeah, because I've got a 4 on the bottom. Ah, you did good.
Algebra. Algebra.
3 moles of water are produced. So now, how do I find the partial pressure of my water? We're going to use PivNert. And instead of having 2 moles, now we have 3 moles.
Oh, jeez.
Oops, where's the pen? 3 moles of water instead of 2. So
And
the
then
pressure of
everything else will
H2O,
remain the same.
yep, everything else is going to be the same. You notice how we're getting really efficient at doing the math that is easy. That's the kind of math I like to do. So we got 2.41 there?
2.42.
Okay, 2.42. So we better just call that 2.4 atmospheres. And to find the total pressure by
You're going to
Dalton's
use
law.
Dalton's law again and add up all the pressures.
Okay, let's find a space where we can do that.
There you go, Spunk.
Just
Total
kind of yawn
pressure.
right there, but
It happens.
Oh, did I interrupt you, or is it Amanda who's being rude?
I
Oh,
think
it's
it's
me.
Lindsay.
Sheesh.
Amanda.
Okay, 1.6 plus 2.4, do that in your head.
Whoa, that should be really simple. It is definitely 4.
5.
What? It's definitely 4.
5.
I was really close to saying something.
Wow.
3.7. Or double check.
Oh,
I
boy.
knew it was 4.
Of course, the whole time. Good. Well, I'm glad you looked back to see, did we answer the question they asked? That's one of our most common mistakes, right? Is to think you're done with a problem, but you really did not even answer the question they asked.
And then it takes more work to get there.
Hooray, now we can erase everything.
Now, okay, are you sure? If not, we can undo, because we found that button.
I
Is it
totally
press
saved
up
your
again?
butt there. Oh, it's
You
that
did.
one.
Movement.
Okay. Yes.
All right. Movement of gases. Now, you said I can get my arrows back. Yay! There they are. Click the pen.
Click the thing.
All right. Let's talk. Let's talk about how gases move. One thing gases could do is to effuse, which basically means to leak out. They escape from the hole in the container, and that's called effusion.
Is that what that little red one did? We had 88 little red particles,
Yeah.
and all of a sudden we had 87.
Yeah, exactly. When our number of particles dropped from 88 to 87, and we did not know why, it was probably effusion. One of them escaped. And here's our rule. Smaller particles escape faster than big particles because, in general, if you have two particle sizes, one guy that's big and one guy that's small, in molecules and atoms, the skinny guy wins the race. And the fat guy can't run as fast.
You ready for this?
I'm ready.
Pooh Bear cannot fit through the hole as fast as Piglet could.
There you go.
So any of you who likes Winnie the Pooh,
Now we know.
now you know.
Yep. Pooh Bear
Know the
does not
truth.
fit through the hole as well as
He gets
Piglet.
stuck, remember? And Christopher Robin has to come and
Yes.
pull him out.
He does. Let's look at our example here. We still have our mixture of gases. So if we open this container a little bit,
Just a wee bit.
then let's watch how many particles there are. And we went from 121 of the red particles, and now we're already down to like 86. Yeah, let's open it bigger, because this would take forever. Where's my mouse?
It's right.
I can't even
It's right
see
there.
it.
It's right
I
there.
just saw it. It's right there. It's right there.
Oh.
Up, 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 up.
Yay!
Yeah.
Arrows.
I like how
Okay.
they saw you pointing, Lindsay.
There,
Oh,
well,
God.
I saw. That was the important part. Okay, so watch this number over here that tells us how many particles we have. So see right here? Which one's going down faster?
The red one.
The red one.
Smaller one.
Because we started with 121 red particles, right? And 88 blue particles. So the red's definitely getting smaller faster because it's leaking out faster than the blue. All right, well, that is called Graham's law of effusion. And Graham says the skinny ones effuse at a faster rate than the fat ones.
The graham crackers.
In fact, we learned this equation to tell us how much faster. So the rate of your first gas compared to the rate of your second gas, which is not on there, is equal to the square root of the molar mass of your second gas divided by the molar mass of your first. All right, so see, 2 was on bottom and now it's on top. And
And
the
then
1 went
R
on
was
top
on-
and that goes on the bottom.
It's on top.
Yep, and so we're going to do a demonstration in class where we get to actually see this happen. The small particle moves faster than the big particle. Let's wrap this up because this is it for our podcast. Diffusion is not quite the same as effusion. Whoops, I thought I could get rid of that. Oh well, we'll just leave it there. Diffusion tells us how a gas spreads out in a space. So it's in a container, and it's going to fill up the entire container. And it's always going to move from an area of high pressure to an area of low pressure. And you probably heard about that in biology class, right? When you talked about how particles move from one place in a cell to the other, or moving across the cell membrane by passive diffusion.
Yep.
Yeah, so it can just move as long as it's going from high to low. And that's what gases do too. The smaller the particle is, the faster it diffuses. And so now let's look at that. Oh, I went past it. I hate it when that happens. All right, so we're going to reset this for a different experiment now. Reset.
And you have your writing still on there.
My writing's still on there. Okay.
It's okay.
You can't really see
Can't
it.
see it.
Yeah, black on the black. All right, so now let's put some gas in there. And what we know is that it's all going to start in one area, right here where it comes in. And I can't even see that little spark. And then it spreads out throughout the entire container. The heavy one was easier to see, I think, because when we pump it in,
It goes really
Slow.
slow.
yeah, then it's easier to see how it starts to spread everywhere. Diffusion is a really important concept in your body. That's how cells get differentiated, so that your body knows which end of the embryo should be the head and which end of the embryo should be the tail. And so when a protein is produced on one end of the cell, if it all spread out equally, evenly at the same rate, we wouldn't know which end is which. So let's say here's a cell. You're making the protein over here on this part of the endoplasmic reticulum at these ribosomes on this side, right? And then that protein can distribute. It's going to have higher concentration on this side at first than it does over here. This would be in really low concentration. And that's going to stimulate certain reactions to take place. They get to a critical concentration, and we know, hey, this is going to be the head side of the baby, and then here's where we have to make arms and legs. Right? It kind of looks like a baby turtle. Right. Oh well. Yeah. Yeah, because you need this to take place. You got to have diffusion, or you would just be a butthead, because we can't tell which end is which.
Lindsay?
Yep. Be nice. Be nice. Okay, guess what? We're done. Oh, there's the baby turtle still. Nope, there's our blank slides where we did our example problems. We're going to do these homework problems. You can try them at home if you like, or you can wait till you're in class and you have our support to do this. But that's it for all of this unit. Unit 9 is done, folks. Thanks for
Awesome.
your help, ladies. We appreciate it very much.
Sure thing.
Okay, how do I stop this thing? Record. There it is. No, that's not it. Make it stop.
You have to edit it out.
Yeah,
Where'd it go?
I can't edit it because
Stop.
this doesn't work. Stop. You should sing a song.
No.
Or dance.